Our reality may be the most convincing illusion in the cosmos. This is the startling claim of the holographic principle, a radical idea from the edge of physics. It asks us to consider a question that reshapes everything. Is the universe we experience, with all its vast depth and tangible solidity, nothing more than a grand projection? Could every star, every planet, and every one of us be a kind of cosmic mirage, encoded on a distant, two-dimensional surface like data on a vast celestial film? By the end of this exploration, you will understand how this incredible idea emerged from the fiery paradoxes of black holes and the strange realms of string theory, fundamentally altering what we think is real. We will journey from the solid ground of classical physics to the disorienting possibility that our three-dimensional world is a holographic illusion. How could something as fundamental as space itself be a trick of the light? For centuries, our understanding of the cosmos was built upon a foundation that felt as solid as the ground beneath our feet. The great Isaac Newton envisioned the universe as a grand, silent theater. In this view, space itself was the absolute and unchanging stage, a vast, empty, three-dimensional container that simply existed. It was the background against which the celestial drama of planets and stars played out, but it was passive and rigid. You could move through it, measure it in length, width, and height, but you could not affect it. This stage was eternal and immutable, providing a fixed coordinate grid for all of reality. This intuitive, classical picture is deeply embedded in how we perceive the world. When you reach for a cup, you are navigating this three-dimensional arena. When you watch a bird fly, you are tracking its path through this silent, invisible framework. It is the canvas of our existence, and for a long time it seemed unquestionably real. Then came Albert Einstein, who transformed our understanding in a profound way. With his theory of general relativity, Einstein proposed that space was not a rigid stage at all. Instead, he wove space and time together into a single, dynamic entity called spacetime. Think of it not as a static container, but as a vast, flexible fabric. This fabric is not just a backdrop, it is an active participant in the cosmic dance. The presence of mass and energy, like a planet or a star, causes this fabric to curve and warp. That curvature is what we experience as gravity. A planet orbits a star not because it is being pulled by a mysterious force, but because it is following the natural contours of this curved space-time, like a marble rolling around a dip in a stretched sheet. This was a monumental shift. Space became something that could bend, stretch, and even ripple, sending out gravitational waves across the cosmos. Yet, for all its revolutionary dynamism, Einstein's universe remained at its heart a three-dimensional world. Or more precisely, a four-dimensional one with time as the fourth dimension. But the spatial dimensions, the up-down, left-right, forward-backward of our experience, were still fundamentally real. The fabric might be warped, but it was still a fabric with genuine depth and volume. General relativity gave us a universe that was malleable and interactive, but it was still a universe of something, a substantial, dimensional reality. This elegant framework became the bedrock of modern cosmology. It explained the motion of galaxies, the bending of light around massive objects, and the expansion of the universe itself. It described a cosmos where space-time is the ultimate canvas, and everything within it, from the smallest particle to the largest galaxy cluster, is painted upon that canvas. This was the established, powerful, and beautiful picture of reality, a picture that felt complete. It was the definitive before snapshot, the solid ground of understanding from which the next, even more radical, leap would have to launch. And that leap would begin not in the vastness of space, but in the absolute darkness of its most mysterious objects, black holes. Black holes were the perfect storm. These cosmic anomalies, predicted by Einstein's own equations, became the ultimate testing ground for our understanding of reality. They are regions of space-time so warped by gravity that nothing, not even light, can escape their grasp. For decades, they were thought to be simple, silent, and eternal in points. Whatever fell in was gone forever. Its information, the specific arrangement of particles that made it what it was, seemingly erased from the universe. This was a comfortable idea within the classical framework of general relativity. But then, in the 1970s, Stephen Hawking applied the strange rules of quantum mechanics to the edge of a black hole, and everything changed. He made a shocking prediction. Black holes, he argued, are not completely black. Due to bizarre quantum effects occurring right at their boundary, known as the event horizon, they should slowly leak a faint glow of particles. This is Hawking radiation. Over unimaginable stretches of time, this slow leak would cause the black hole to evaporate, eventually vanishing entirely. This was a monumental discovery, linking gravity and quantum theory in a new way, but it created a catastrophic problem, now known as the black hole information paradox. Here is the contradiction. The bedrock principle of quantum mechanics is that information is never truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved. Think of burning a book. The paper and ink turn to smoke and ash, a seemingly chaotic mess. Yet, in principle, if you could track every single particle of smoke and measure every bit of heat with perfect precision, you could theoretically reconstruct the book. The information of every word on every page still exists in the universe, just in a different, more disorganized form. Quantum mechanics insists the universe always keeps perfect records. But Hawking's calculations suggested something very different for black holes. In his original model, the radiation leaking out was purely random, like static. It carried no specific details about what fell in. A black hole formed from a collapsed star would emit the same pattern of radiation as one formed from 1,000 antique pianos. Then, when the black hole finally evaporated and disappeared, all the specific information about the star or the pianos would be lost forever. Poof, gone. This presented physics with an impossible choice. Either quantum mechanics was wrong and information could be destroyed, which would unravel the entire framework of modern physics. Or general relativity was incomplete, failing to describe what truly happens at the most extreme scales. This was not a minor puzzle. It was a fundamental contradiction at the heart of our understanding of the cosmos, a glaring signal that our picture of reality was missing something profound. The desperate search for a solution to this paradox is what ultimately led physicists to a startling and elegant possibility, one that would reframe the very nature of space itself. The solution to this paradox began with a question that seemed almost absurd. What if the key to understanding a black hole's immense gravity and its hidden information was not found in its dark, fathomless interior, but on its skin? This is the profound insight that came from a young physicist named Jacob Bekenstein. He was grappling with a strange connection between black holes and one of the most fundamental concepts in physics, entropy. In everyday terms, entropy is a measure of disorder or randomness. A tidy room has low entropy, a messy one has high entropy. But in thermodynamics, it is more precisely a measure of the number of microscopic ways a system can be arranged while still looking the same from the outside. It is, in essence, a count of hidden information. A melted ice cube has higher entropy than a solid cube because the water molecules can be arranged in many more indistinguishable ways. Bekenstein made a daring leap. He proposed that a black hole must also have entropy. This was radical because entropy was a property of matter and energy, and a black hole was supposed to be a simple, featureless void. But if it had entropy, he reasoned, it must have an enormous amount of hidden information locked away, and then he made the calculation that changed everything. He found that the entropy of a black hole, and therefore the total information it could contain, was not proportional to its volume. It was not about how much three-dimensional space was inside the event horizon. Instead, it was directly proportional to the surface area of the event horizon itself. Think of it this way: imagine a vast library. In a normal, three-dimensional world, the amount of information the library holds, the number of books, would depend on the size of its rooms, its volume. But Bekenstein was suggesting that for a black hole, the information capacity was like writing every single word from every single book onto the two-dimensional surface of the library's walls. The interior space, the volume, became almost irrelevant. The boundary held the code. Stephen Hawking initially resisted this idea, but his own work on Hawking radiation led him to confirm and refine it. He derived the exact, beautiful formula: the entropy of a black hole equals 1/4 of the area of its event horizon, measured in tiny, fundamental units called Planck areas. This was not a vague metaphor. It was a precise mathematical relationship written into the laws of physics. The implication was staggering. It meant the maximum amount of information, the ultimate complexity or detail, that any region of space can possibly hold is not determined by how much stuff you can pack into its volume. It is limited by the area of the surface that encloses it. This turns our intuition inside out. In our daily experience, a bigger box can always hold more things than a smaller box. But at the most fundamental level of reality, according to this black hole thermodynamics, the contents of a three-dimensional region are somehow dictated by its two-dimensional boundary. It was as if the universe itself was whispering a secret. The true degrees of freedom, the fundamental data that makes up reality, might not be spread throughout the volume of space like ingredients in a cake. They might be painted like a cosmic barcode on the surface at its edge. This was the first crucial clue that our three-dimensional experience could be a magnificent illusion, a holographic projection from a simpler, two-dimensional reality where all the real information actually lives. This discovery was a mathematical whisper, a clue hidden in the equations of black holes. But whispers can become shouts. In the early 1990s, two brilliant physicists, Gerard Hooft and Leonard Susskind, took this clue and ran with it into the heart of theoretical physics. They asked a question that was both simple and utterly revolutionary. What if this bizarre area law for information was not just a strange property of black holes? What if it was a fundamental law of the universe itself? From this question, the holographic principle was born. The core claim is as elegant as it is mind-bending. It proposes that all the information contained within any volume of space, any region you can imagine, can be fully described by a theory that lives on the lower dimensional boundary of that region. Think of a room. In our normal view, the room is a three-dimensional space filled with air, light, dust, and furniture. Every detail exists within that volume. The holographic principle suggests a different picture. It says that every single bit of information about everything inside that room, the position of every dust mote, the wavelength of every photon of light, the shape of every piece of furniture, is not truly stored inside the room at all. Instead, it is perfectly encoded on the two-dimensional walls, floor, and ceiling that surround it. The three-dimensional interior, with all its rich depth and solidity, is a projection. The real data, the ultimate source code, exists on the enclosing surface. This is where the name comes from, and the analogy is powerful. A hologram, like the kind you might see on a credit card or in a museum display, is a flat, two-dimensional piece of film. But when you shine a laser through it, a stunning, three-dimensional image appears in the space above it. The film itself is just a pattern of microscopic interference lines, a two-dimensional code. Yet it contains all the information necessary to reconstruct a complete three-dimensional scene. The holographic principle applies this logic to the cosmos. It suggests our universe, with its galaxies, stars, and planets, might be a cosmic hologram. The three-dimensional reality we move through and touch could be a magnificent projection from a vast, two-dimensional surface at the edge of everything we can observe. Hooft and Susskind were not merely suggesting a new property of space, they were proposing a new paradigm. The black hole was not an exception to the rules. It was the clearest example of the rule, a place where the illusion becomes thin enough for us to glimpse the machinery behind it. By transitioning from a black hole-specific result to a universal principle, they reframed the very nature of reality. Space, with its comforting depth, might not be a fundamental ingredient. It might be an emergent phenomenon, a side effect of information processing on a distant, flat screen. This transforms the information paradox from a catastrophic problem into a potential key. If the information of what fell into a black hole was never truly inside its volume to be lost, but was always safely stored on its event horizon surface, then there is no paradox at all. The information was never destroyed, it was just translated. The evaporation of the black hole via Hawking radiation becomes the slow, careful readout of that surface data back into the universe. The principle solved a deep puzzle, but in doing so, it presented an even deeper mystery. If this is true, then what or where is the cosmic film, and what kind of projector could possibly bring such an illusion to life? A bold idea needs a mathematical backbone. For the holographic principle to move from a fascinating speculation to a serious description of reality, it required a precise working model. This is where the most ambitious framework in modern physics, string theory, entered the stage. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy or strings. Different vibrations of these strings correspond to different particles, like electrons or photons. To make the math of these vibrating strings work consistently, the theory demands extra dimensions of space, curled up into sizes far smaller than an atom. While this made string theory notoriously complex, it also provided a rich, multidimensional playground where radical ideas like holography could be rigorously tested. The breakthrough came in 1997 from a young physicist named Juan Maldacena. Working within string theory, he discovered a precise and astonishing mathematical equivalence, now known as the anti-de Sitter conformal field theory correspondence, or AD-SCFT for short. This mouthful of a name describes something profoundly elegant. Maldacena showed that a particular type of string theory, which includes gravity, operating in a specific five-dimensional warped space called anti-de Sitter space, is completely and exactly equivalent to a different kind of theory living on the four-dimensional boundary that encloses it. This boundary theory is a conformal field theory, a quantum theory that describes particles and forces like the ones in our standard model, but crucially, it does not include gravity at all. Let us unpack what this means, because it is the concrete heart of the holographic principle. Imagine a vast, empty cosmic sphere. Inside the sphere, the laws of physics include gravity, warped space, and all the strange phenomena that come with it, described by strings vibrating in 5 dimensions. Now paint the inner surface of that sphere with a theory of quantum particles that interact with each other, but where gravity simply does not exist. It is a flat, gravity-free world of pure quantum information. Maldacena's equations proved these two descriptions, the gravitational world inside the volume and the quantum world on the surface, are not just similar. They are two different languages describing the exact same physical reality, a process involving black holes and gravitational waves in the interior can be perfectly translated into a complex dance of quantum particles on the boundary, and vice versa. One is a holographic projection of the other. This was not a philosophical suggestion. It was a precise, calculable, mathematical dictionary. Physicists could take a notoriously difficult problem involving gravity in the five-dimensional world, translate it into a potentially simpler problem involving quantum particles on the four-dimensional boundary, solve it there, and then translate the answer back. This technique has become an incredibly powerful tool, offering insights into problems ranging from the behavior of exotic states of matter to the very early moments of the Big Bang. The AD-SCFT correspondence provided the first solid, working example that the holographic principle could be a consistent, logical feature of a physical theory. It transformed holography from a compelling conjecture into a rigorous framework that physicists could actually use. It showed that a universe with gravity could indeed emerge, like a three-dimensional image from a flat film, from a world where gravity is not fundamental, but is instead a consequence of quantum information interacting on a lower dimensional surface. This discovery sent a shockwave through the theoretical world, offering a tantalizing glimpse of how our own universe might be constructed, but it also raised an immediate and pressing question. If our reality is a hologram projected from some distant boundary, where exactly is that cosmic screen and what is written upon it? Maldacena's discovery gave us a map, but to understand the territory, we need to look at its two astonishingly different landscapes. On one side of this cosmic duality, we have the bulk. This is the higher dimensional world, the interior of our imagined sphere. In the specific model, it is a five-dimensional space with a peculiar, warped geometry called anti-de Sitter space. Think of it as a vast, cosmic saddle shape that curves inward on itself. This is the realm where gravity reigns supreme, where strings vibrate across extra dimensions, and where phenomena like black holes can form and evolve. It is the world that at first glance seems to have genuine depth and volume. It feels like a place. Now paint the absolute outermost layer of this bulk, the skin of the sphere. This is the boundary. It exists at a lower dimension, one less than the bulk. In our model, if the bulk is five-dimensional, the boundary is four-dimensional. This boundary is not a physical barrier you could touch. It is more like the ultimate edge of that reality, a surface where a completely different set of laws applies. Here, there is no gravity. Instead, this boundary is home to a conformal field theory, a type of quantum theory that describes particles and forces interacting without any reference to the curvature of space. It is a flat, frenetic world of pure information and quantum entanglement. The magic, the true heart of holography, is that these are not two separate worlds. They are one and the same reality, described in two radically different languages. Every single event, object, or process in the bulk has a perfect, unambiguous translation on the boundary. It is a precise dictionary written in the language of mathematics. For example, take a star collapsing to form a black hole in the five-dimensional bulk. From our perspective inside that bulk, it is a gravitational cataclysm, warping space-time into a one-way trap. But translate that event through the holographic dictionary to the four-dimensional boundary. There, the exact same physical situation is described not as a hole in space, but as a specific state of the quantum matter living on that surface. Specifically, it corresponds to the boundary theory heating up to an incredible temperature and reaching a state of thermal equilibrium, like a super-hot, dense plasma. The black hole's properties, its mass, its temperature, even its mysterious entropy, are all encoded in the thermal and quantum properties of that boundary plasma. A falling object approaching the black hole's event horizon in the bulk might be translated as a quantum particle on the boundary becoming increasingly entangled with that hot plasma state. This is why the holographic principle is so much more than a poetic analogy. It is a calculable, testable framework. Physicists use this dictionary to tackle problems that are otherwise impossible to solve. A question about the chaotic behavior of matter inside a black hole, hopelessly complex in the gravity-filled bulk, can become a more manageable question about quantum chaos on the boundary. Solve it there and you have your answer for the bulk. This establishes holography not as science fiction, but as a serious proposal for how our universe might fundamentally operate. It suggests that the gravity we feel and the three-dimensional space we navigate could be collective illusions, emergent from a vast, flat, quantum computer operating at the edge of everything we know. But this perfect mathematical duality forces a startling conclusion about our own world. If the holographic principle holds true, then the three-dimensional space we experience every single day, with all its solidity and depth, is not a fundamental feature of reality. It is an illusion, a magnificent and convincing projection. The distance to the moon, the volume of a cup, the feeling of moving forward through air, these are not primary truths of the cosmos. They are emergent properties, secondary effects that arise from something far more basic happening on a distant, flat screen. Think of a modern video game, a vast, open world you can explore in 3 dimensions. You see rolling hills, deep canyons, and towering cities. You feel a sense of distance as you travel, and objects have real volume as you interact with them. Yet, all of this rich, three-dimensional experience is generated in real time by lines of code running on a 2-dimensional computer chip. The chip itself is flat. It has no hills, no canyons, no space inside it. It contains only electrical charges and logical operations, ones and zeros. The immersive game world emerges from the incredibly complex relationships and instructions encoded in that flat silicon landscape. In a strikingly similar way, the holographic principle suggests our universe operates. The fundamental reality is the boundary, the cosmic chip, where the basic units of information exist and interact. These are not tiny pixels of a picture, but more like entangled quantum bits, each connected to others in a vast, complex web. It is the nature of these connections, the patterns of correlation and entanglement between all that information, that gives rise to the experience of geometry itself. When the information on the boundary is arranged and correlated in a particular, highly organized way, it generates the perception of a third dimension. Distance in our world, for example, might not be a pre-existing void we traverse. It could be a measure of how weakly or strongly 2 pieces of information on the boundary are entangled with each other. 2 atoms that are close together in our 3-dimensional view would correspond to bits of boundary information that are deeply and directly linked. 2 galaxies far apart would correspond to information that is only very distantly or indirectly correlated. Volume, the amount of space inside an object, could emerge from the total complexity of the information describing that object on the surface. This turns our intuition completely inside out. We are used to thinking that things exist in space, but holography implies that space itself exists because of things, or more precisely, because of the relationships between the fundamental data points of reality. The solidity of your desk, the emptiness of the room around you, the vast gulf between stars, all of it is a kind of collective hallucination, a consistent story told by the underlying quantum code. This is the true philosophical shock of the idea. It means that the most basic stage of our existence, the 3-dimensional arena we have taken for granted since the dawn of human thought, is a derivative phenomenon. It is not the foundation but the grand finale of a deeper, simpler, and flatter process. We are not living inside the universe, we are living inside its projection. The profound question then becomes, if space is an illusion, what does that say about the other great pillar of our experience, the relentless flow of time? The most profound implication of holography is a complete inversion of what we consider to be real. For millennia, we have believed the universe is made of stuff. First it was earth, air, fire, and water, then atoms and molecules, then subatomic particles and force fields. Our entire scientific story has been about identifying the fundamental substances that occupy the container of space and time. But what if we have the story backwards? What if the fundamental substance is not a thing at all, but information? This is the revolutionary idea, often called it from bit, proposed by the visionary physicist John Archibald Wheeler. He suggested that every particle, every force field, and even the fabric of space-time itself ultimately derives from binary yes or no answers from the most basic units of information. In this view, the cosmos is not a collection of objects moving through a void. It is a cosmic computation, a vast network of logical relationships. At the very bottom of reality, beneath the illusion of three dimensions, there may be nothing but quantum bits or qubits. Unlike the simple ones and zeros of a classical computer, a qubit can exist in a superposition, a blend of both states at once. It is a unit of pure potential, of possibility. And according to the holographic principle, the geometry of our world, the very distance between 2 points, emerges from how these qubits on the boundary are entangled with one another. Entanglement is that strange quantum connection where two particles, no matter how far apart in our space, share a single unified existence. Measuring one instantly determines the state of the other. In the holographic framework, this is not just a curious property of particles in space. It is the very thread that weaves space itself into being. Imagine the boundary as a vast, flat tapestry woven from countless entangled qubits. Where the entanglement is strong and direct between two threads, the projection into the bulk creates the experience of closeness. Where the entanglement is weak or indirect, the projection creates vast distance. A single, solid object in our world, like a rock, would not correspond to a cluster of rock-stuffed pixels on the boundary. It would correspond to an incredibly intricate and dense pattern of correlations, a specific symphony of entangled information that, when projected, manifests as a cohesive, three-dimensional form with mass and volume. Gravity, then, ceases to be a fundamental force. In this emerging picture, gravity is not something that acts in space. It is a side effect of the geometry of space, and since that geometry emerges from information, gravity itself becomes an informational phenomenon. It is the holographic universe's way of responding to the complexity and disorder of the information on its boundary. Much like heat is a macroscopic effect of microscopic molecular motion. This transforms our understanding from the ground up. We are not made of matter that has somehow learned to think. We are patterns of information that have learned to feel solid. The chair you are sitting on, the screen you are watching, the air you are breathing, all are magnificent and stable illusions conjured by an underlying quantum reality that is flatter, stranger, and more logical than we ever dreamed. If information is the true bedrock, then what does that say about the most persistent illusion of all, the steady, forward march of time? Time itself may be the final frontier of this great illusion. But to understand how something as intangible as time could emerge, we must first look at the strange quantum glue that binds the very fabric of space together. This glue is quantum entanglement. It is the phenomenon Einstein famously called spooky action at a distance, where two particles become so deeply linked that measuring the state of one instantly determines the state of the other, no matter how far apart they are in our three-dimensional view. For decades, this was seen as a bizarre but isolated quirk of the quantum world, a puzzling connection between objects in space. The holographic principle turns this idea on its head. It suggests entanglement is not happening within space. It is what creates space. The geometric connections we perceive as distance and volume are woven from threads of quantum correlation on the distant boundary. Think of a simple, profound example. Take two particles that are maximally entangled. In our world, they might be light years apart with vast, empty space between them. But in the fundamental quantum description on the boundary, These two particles are not separate entities with a gap. Their information is so thoroughly mixed and correlated that they are, in a very real informational sense, directly connected. They share a single quantum identity. The groundbreaking insight from researchers like Juan Maldacena and Leonard Susskind was to ask what this direct connection on the boundary would look like when projected into the gravitational bulk, the world of space and gravity. Their astonishing answer, a wormhole. In the bulk, the mathematical description of these two entangled particles is not two independent points with empty space between them. It is 2 points connected by a bridge, a tunnel through the geometry of space-time itself. This tunnel, known as an Einstein-Rosen bridge or a wormhole, is the geometric manifestation of quantum entanglement. More entanglement on the boundary corresponds to a shorter, more direct bridge in the bulk. Less entanglement, or if the particles become disentangled, corresponds to the bridge pinching off, leaving two separate regions of space with no connection. This is not science fiction speculation. It is a rigorous mathematical equivalence derived from the holographic dictionary. The glue holding space together, giving it continuity and structure, appears to be nothing more than the sum total of all these quantum correlations on the cosmic screen. The empty void between stars is not truly empty. It is saturated with an invisible web of entanglement, a foundational connectivity that makes geometry possible. This transforms our understanding of dimension from a static given to a dynamic process. A third spatial dimension does not just exist because we label it up, down, or left, right. It emerges because the quantum information on the two-dimensional boundary is organized in a highly specific, correlated way that, when decoded, generates the consistent illusion of depth. It is like the way millions of individual threads, when woven together on a flat loom with precise patterns, can create a tapestry with incredible texture and the appearance of three-dimensional scenes. The threads themselves are flat, but their relationships birth the illusion of space. So, the chair you are sitting on feels solid, not because it is made of solid substance all the way down, but because the quantum information describing it on the boundary is entangled in an incredibly stable, complex pattern. That pattern projects a coherent, persistent form into our perceived world. This makes the emergence of our reality far more mechanistic than magical. It is not a mysterious emergence from nothing, but a logical consequence of information processing according to quantum rules. The universe is not a place where strange things happen. It is the strange thing happening, a constant computation where geometry and perhaps even time are the outputs. If the very structure of space is born from quantum connections, then what does that imply for the structure of everything within it, from the smallest particle to the vast architecture of the cosmos? This brings us back to the original crisis, the black hole information paradox that threatened to tear physics apart. Remember the impossible choice. If information is truly lost when a black hole evaporates, quantum mechanics is wrong. But if information is preserved, where could it possibly be hiding from the all-consuming gravity? The holographic principle provides an elegant and definitive escape from this trap. The solution lies in shifting our perspective entirely, from the three-dimensional drama of the falling object to the two-dimensional data processing on the boundary. From the viewpoint of the cosmic screen, the event horizon, information never actually falls into a black hole in the way we imagine. When a star collapses or any matter crosses that point of no return, its information does not travel inward to a mysterious singularity. Instead, it is instantly and perfectly encoded onto the two-dimensional surface of the event horizon itself. The horizon is not a wall that information hits and is destroyed against. It is the ultimate hard drive recording every single bit of data about what crossed it. The three-dimensional interior of the black hole, with its warped space and crushing gravity, is the holographic projection generated by that specific, incredibly hot and scrambled data on the surface. Now consider Hawking radiation. This is not random noise leaking from a dying void. From the boundary perspective, Hawking radiation is the very process of that encoded information being slowly, carefully read back out. The surface data, which is in a state of maximum disorder or maximum entropy, gradually decodes itself. It reorganizes, translating itself from a scrambled thermal state on the horizon back into the particles and energy that radiate away into the universe. The black hole shrinks not because it is losing mass in a simple way, but because it is effectively erasing its own hard drive, pixel by pixel, as the information is retrieved. By the time the black hole evaporates completely, all the original information that formed it has been faithfully returned to the cosmos, albeit in a highly transformed and diffused state. It is like taking a beautifully intricate sculpture, grinding it into a pile of fine, seemingly identical dust, and then using a perfect recipe to reassemble the sculpture from that dust. The information was never gone, it was just in another form. This resolution is not just a clever fix, it is a profound demonstration of the holographic principle's power. It took a problem that seemed utterly intractable within our old, three-dimensional way of thinking and solved it by changing the very stage on which the drama was set. The principle showed that by taking the boundary description seriously as the more fundamental reality, the paradox simply melts away. This success gave the idea immense credibility. It moved holography from a speculative what-if to a compelling framework that could genuinely reconcile the two great pillars of modern physics, quantum mechanics and gravity. Solving such a deep paradox hinted that this radical view of reality might not just be mathematically beautiful, but might actually be true. Yet for all its mathematical elegance, the ad-SCFT correspondence presents a profound puzzle for cosmologists. It describes a universe that is fundamentally different from our own. The model operates within a specific type of space called anti-de Sitter space, a cosmos with a geometry that curves inward on itself, like the inside of a vast cosmic saddle. This geometry is defined by what physicists call a negative cosmological constant. It is a self-contained, stable, and ultimately static kind of universe. But when we look up at the night sky, our universe tells a different story entirely. Observations of distant supernova and the cosmic microwave background reveal a cosmos that is not static, but expanding at an accelerating rate. This accelerating expansion is driven by a positive cosmological constant, a form of dark energy that pushes space itself apart. Our home is not an anti-de Sitter space. It is what mathematicians call a de Sitter space, a universe destined to expand forever into a cold, thin, and increasingly isolated future. This is not a minor detail. It is the central challenge of applying holography to reality. The beautiful, working dictionary of ad-SCFT was built for a universe that behaves in the exact opposite way to the one we actually inhabit. So, the million-dollar question becomes, can we build a similar holographic dictionary for a de Sitter universe? The search for a d-SCFT correspondence is one of the most urgent and difficult frontiers in theoretical physics. The problem is extraordinarily complex. In an expanding de Sitter space, the natural boundary of the universe is not a fixed, distant wall you can point to. It is a horizon, much like the event horizon of a black hole, but one that surrounds us due to the accelerated expansion. Information can be lost beyond this cosmic horizon, just as it seems to be lost behind a black hole's event horizon. This makes constructing a precise, dual quantum theory on that boundary incredibly tricky. If ad-SCFT is like having a perfect translation guide between two known languages, then finding d-SCFT is like trying to decipher one language when we only have vague, fragmented hints about the other. Researchers are exploring many creative avenues. Some propose that our accelerating universe might be described by a quantum theory that is inherently unstable or lives in a lower number of dimensions than we expect. Others suggest the dual theory might involve exotic mathematical properties that seem unfamiliar or non-physical from our current perspective. The work is ongoing, a testament to the difficulty of the problem. This limitation is crucial to acknowledge. It means that while the holographic principle offers a breathtakingly powerful and consistent framework, and while it has brilliantly solved puzzles in toy model universes, we do not yet have the specific dictionary for our own cosmic story. We have seen the stunning potential of the idea, but the final, definitive chapter that directly describes the stars above us remains unwritten. It is the crucial gap between a magnificent theory and an applied description of our home. This gap, however, does not diminish the principle's revolutionary insight. Instead, it frames our current understanding. We have discovered a profound new way that reality could be structured. The task now is to see if our particular universe chose that path. And to answer that, we must look for clues not just in the equations, but in the very fabric of the cosmos we can observe. The ultimate test of any radical idea lies not in its mathematical beauty, but in whether it leaves a fingerprint on the real world. For the holographic principle, the challenge is immense. We are searching for evidence that the universe is a projection, that space itself has a fundamental resolution limit, like the pixels on a screen. How could we possibly detect the graininess of reality? Scientists are pursuing several ingenious paths, looking for subtle whispers in the cosmos that might betray the holographic code. One promising avenue looks back to the very beginning, to the afterglow of the Big Bang itself, known as the cosmic microwave background radiation. This faint, uniform light that fills the sky is a snapshot of the infant universe, and it contains incredibly tiny fluctuations in temperature. These fluctuations are the seeds from which all galaxies and cosmic structures eventually grew. Researchers hypothesize that if space-time has a fundamental pixelation at the Planck scale, it would have imposed a subtle limit on how tightly packed these early quantum fluctuations could be. It would be like trying to draw an ultra-high-resolution image on a canvas that is itself made of a finite grid of threads. The pattern would show a faint signature of that underlying grid. By analyzing the precise statistical patterns in the cosmic microwave background, astronomers are searching for any deviation from the predictions of smooth, continuous space. While no definitive signal has been found yet, this cosmic fossil remains one of our most powerful windows into the universe's most fundamental architecture. Another frontier is the emerging field of gravitational wave astronomy. When massive objects like black holes collide, they send ripples through the fabric of space-time itself. These gravitational waves are now being detected by observatories like LIGO and Virgo. The holographic principle suggests that if space-time is emergent from quantum information, then these ripples might not travel through a perfectly smooth medium. Instead, they might propagate through a medium with a tiny, inherent graininess, like sound waves moving through air made of discrete molecules. This graininess could introduce a specific, faint type of noise into the gravitational wave signal, a subtle hiss superimposed on the clean chirp of the collision. Detecting such an effect is far beyond our current technological sensitivity, but as our detectors become more and more advanced, scientists will be listening for this whisper of a pixelated reality. Perhaps the most accessible tests come not from giant telescopes, but from tabletop experiments here on Earth. Physicists are creating analog systems using ultra-cold atoms, superconductors, or networks of lasers, which are carefully engineered to behave according to the mathematical rules of holographic duality. These are not miniature universes, but sophisticated quantum simulators. By studying how entanglement and information flow in these controlled, lower-dimensional systems, researchers can observe phenomena that are mathematically equivalent to the emergence of geometry, and even gravitational effects in the higher dimensional projection. When a simulated black hole's information appears to be preserved in the boundary description of such a system, it provides a tangible, laboratory demonstration that the holographic principle's logic holds in a real, physical setup. These experiments show that the idea is not just abstract philosophy, but a framework that makes concrete, testable predictions about how quantum information can give rise to the illusion of space. Each of these paths, from the echoes of the Big Bang to the quiet hum of a quantum simulator, reinforces a crucial point. The holographic principle is not untestable mysticism. It is a scientific hypothesis that makes specific, if extraordinarily subtle, predictions about how our universe should behave at its most fundamental level. The search for its signature is a painstaking process of listening to the faintest signals in the data, a testament to our desire to understand not just what the universe is, but how it is built. Yet, just as the holographic principle seemed to solve one paradox, it helped reveal another, even more baffling one. This newer puzzle strikes at the very heart of what happens at the edge of a black hole, and it is called the Firewall Paradox. To understand it, we must hold two fundamental ideas in our minds at once and see how they violently clash. The first idea comes from Einstein's general relativity, specifically the equivalence principle. This principle assures us that for someone falling into a black hole, crossing the event horizon should be an uneventful, smooth experience. There is no special marker, no brick wall, no dramatic sign announcing the point of no return. If you were falling feet first toward a supermassive black hole, you would not feel anything particularly strange as you passed the horizon. It is just empty space. The second idea comes from the bedrock of quantum mechanics, a rule called the monogamy of entanglement. This rule states that a single quantum bit of information, a qubit, can be deeply entangled with only one other partner at a time. It cannot be perfectly and fully entangled with two separate things simultaneously. This is a fundamental limit on quantum relationships. Now, let us apply holographic reasoning to see the conflict. From the outside perspective, we know that Hawking radiation is emitted from just outside the event horizon. For this radiation to carry away the information of what fell in, as holography requires, each particle of Hawking radiation must be entangled with the interior of the black hole. It is this entanglement that encodes the information, but here is the catch. Quantum field theory also tells us that this same particle of Hawking radiation, because it is created in a pair with a partner particle that falls into the black hole, must also be entangled with that interior partner. This sets up a quantum triangle. The Hawking particle outside seems to need to be entangled with both the interior of the black hole as a whole to preserve information and with its specific partner particle that fell in. This appears to violate the monogamy of entanglement. One particle cannot have two perfect quantum marriages. To resolve this, physicists found a grim possibility. The only way to satisfy the monogamy rule is for the entanglement between the Hawking particle and its infalling partner to be severed or broken at the horizon. But in quantum mechanics, violently breaking a deep entanglement is not a quiet process. It releases a tremendous amount of energy. The consequence, instead of a smooth, empty space at the event horizon, there would be a blistering wall of ultra-high energy particles, a literal firewall that would incinerate anything trying to cross. This presents a brutal either-or choice that no one wants. Either we abandon the equivalence principle and accept that black holes have a fiery, destructive boundary, which overturns a cornerstone of general relativity. Or we abandon the monogamy of entanglement or the purity of quantum mechanics, which would unravel the foundations of that field. The Firewall Paradox shows us that stitching quantum theory and gravity together, even with the powerful thread of holography, is not yet a seamless garment. Deep, puzzling seams remain, reminding us that every answer in physics tends to uncover a new, more profound layer of questions. the Firewall Paradox is a stark reminder that our journey is far from over. Yet, even amid such deep puzzles, the holographic principle stands out as perhaps the most promising path we have toward the ultimate goal of physics, a complete theory of quantum gravity. For over a century, we have lived with a divided reality. Quantum mechanics rules the world of the very small with its probabilities and entanglements. General relativity governs the cosmos of the very large with its curved space-time and black holes. Each is spectacularly successful in its own domain, but they are written in incompatible mathematical languages. Where they meet at the center of a black hole or the first instant of the Big Bang, our equations break down into nonsense. We need a unified theory, one that seamlessly blends the quantum and the gravitational. Many brilliant approaches are trying to solve this puzzle. Loop quantum gravity, for instance, suggests that space itself is woven from tiny, discrete loops, a fabric of finite threads. Causal set theory proposes that reality is fundamentally a vast collection of discrete events, with only their causal relationships creating the illusion of a continuous space-time. These are profound ideas, but they share a common strategy. They attempt to quantize gravity, to take Einstein's beautiful classical theory of curved space-time and break it down into discrete quantum pieces, much like we did with the electromagnetic force to create quantum electrodynamics. The holographic principle takes a radically different, almost backwards approach. It does not try to quantize gravity at all. Instead, it makes gravity disappear from the fundamental description. Remember the core of the AD-SCFT correspondence. The true, fundamental reality is the boundary, a quantum system of particles and fields that does not include gravity in its list of ingredients. Gravity and the three-dimensional space it warps are not fundamental forces to be quantized. They are collective illusions. They emerge like the three-dimensional image from a flat hologram, from the complex, entangled interactions of that gravity-free quantum data. In this view, asking what is the quantum of gravity might be like asking what is the quantum of a whirlpool. A whirlpool is not a fundamental substance. It is a behavior that emerges from the collective motion of countless water molecules. You would not look for a whirlpool particle. You would study how the laws of fluid dynamics arise from the underlying physics of H2O. Similarly, holography suggests we should not look for a graviton, a hypothetical particle of gravity, as a fundamental building block. The effects of gravity would be what we see when the underlying quantum information on the boundary is arranged in a particular, highly entangled way. This reframes the search for a theory of everything from an unexpected and elegant angle. The ultimate theory may not be a single set of equations describing all forces and particles in our four-dimensional world. It might be a quantum theory of information living on a lower dimensional surface, a theory that doesn't mention gravity, space, or even dimensions as we know them at all. The universe we experience, with all its forces including gravity, would then be a magnificent and self-consistent output of that deeper computation. This makes holography not just another candidate in the race, but a complete paradigm shift in how we conceive the problem. We are no longer trying to force two incompatible descriptions to marry. We are searching for the single, simpler parent theory from which both children, quantum mechanics and general relativity, are born. This thermodynamic connection offers a breathtakingly simple way to view gravity. Imagine you're standing outside on a warm day, feeling the heat radiate from the pavement. That warmth is not a fundamental force, it is an emergent property. It arises from the collective, frantic motion of countless molecules. The temperature and pressure you feel are statistical averages, descriptions of the whole, not the individual parts. Remarkably, some physicists propose that gravity itself might be exactly the same kind of phenomenon. It may not be a fundamental force woven into the universe's fabric, but a collective, statistical effect, an illusion that emerges from the chaotic churn of something more basic. This revolutionary idea is known as emergent gravity, and it provides a stunning bridge between the holographic principle and the laws of heat. The story gained its first major mathematical footing in the 1990s through the work of physicist Ted Jacobson. He started with a profound question. What if the most celebrated equation in all of physics, Einstein's field equation of general relativity, was not a fundamental law of the cosmos, but a consequence of something else? Jacobson took the well-established laws of thermodynamics, the science of heat and energy, and applied them not to a gas or an engine, but to the fabric of space-time itself. Specifically, he focused on local horizons. A horizon is any boundary beyond which information is hidden from an observer. The event horizon of a black hole is the most famous example, but even the cosmic horizon created by the expansion of the universe, or the simple horizon you create by accelerating through empty space, qualifies. Jacobson proposed that for any small patch of such a horizon, the fundamental thermodynamic principle must hold. This principle states that when you add a tiny bit of energy to a system, it increases its entropy by an amount proportional to the energy divided by the temperature. It is a universal rule for anything that can hold heat. He then made a brilliant conceptual leap. He reasoned that when matter or energy passes through a local patch of space-time, it disturbs a horizon nearby. That disturbance is equivalent to adding a little bit of energy to that horizon. If the horizon obeys this basic thermodynamic law, then its entropy must increase accordingly. From this single, elegant assumption, applying the thermodynamic law to countless tiny patches of horizons everywhere in space, Jacobson performed a mathematical derivation. The result was not a new law. It was Einstein's field equation, the very heart of general relativity, emerging perfectly from thermodynamic principles. Gravity was not the input, it was the output. Think of it like this. You can study the behavior of a gas by tracking the position and velocity of every single molecule using Newton's laws of motion. That is a fundamental, a microscopic description, but you can also describe the gas perfectly well using macroscopic, statistical concepts like temperature and pressure without knowing anything about individual molecules. The pressure of the gas is not a fundamental force, it is an emergent collective effect of all those molecular collisions. Jacobson's work suggested that Einstein's equations are the pressure of space-time. They do not describe a fundamental force, but the large-scale, statistical behavior of whatever the underlying microscopic constituents of reality are. This was a monumental shift in perspective. It implied that space-time itself has a microstructure, just as a gas is made of molecules, and that this microstructure has properties like entropy and temperature. When you zoom out, the statistical average of all that microscopic chaos looks exactly like the smooth, curved geometry of general relativity. This thermodynamic view of gravity finds a perfect home within the holographic principle. Remember, in holography, a volume of space with gravity is dual to a quantum system without gravity living on its boundary. That boundary system is a thermal system. It has a temperature and an entropy. The work of Jacobson and others shows that the gravitational equations in the bulk are simply a translation of the thermodynamic laws governing that boundary. The force of gravity we feel is, in this framework, an entropic force. It is not a pull in the traditional sense, but a tendency for the universe to move toward states of higher entropy or greater disorder on its fundamental screen. A famous analogy proposed by physicist Eric Verland is to think of a polymer chain like a strand of DNA coiled in a solution. If you try to stretch it out, it will resist. This is not because there is a fundamental contractile force between the molecules. It is because the coiled state has many more possible microscopic configurations. It has higher entropy. The chain naturally resists being pulled into a more ordered, lower entropy straight line. The force you feel is entropic, a statistical preference for disorder. In a similar, though vastly more complex way, gravity might be nature's tendency to maximize the entropy associated with the information on the cosmic horizon. An object falls not because it is being pulled, but because the total entropy of the universe increases when it moves toward a massive body, rearranging the information on the boundary in a more probable way. This perspective elegantly reinforces the core holographic revelation. If gravity is thermodynamic and emergent, then the space-time it curves cannot be fundamental either. They are both secondary, large-scale descriptions of a deeper, frenetic, and likely lower-dimensional reality. We are not living in a universe of forces and fields, but in the statistical shadow of a vast, cosmic computation where information is the only true currency. The universe may have a resolution limit. This startling implication flows directly from the holographic principle's core mathematics. If the total information in any region is capped by its surface area, as the Bekenstein-Hawking formula dictates, then space-time cannot be a perfectly smooth, continuous fabric. It must be woven from discrete, fundamental units of information, like a cosmic tapestry made of individual threads. There is a smallest possible piece, a pixel of reality. This ultimate pixel is known as the Planck area. To understand its significance, we need to look back at that pivotal equation. The entropy of a black hole, which counts its hidden information, equals 1/4 of the area of its event horizon measured in these tiny squares. Each Planck area, roughly 10 to the power of -70 square meters, can hold just about one fundamental unit of information, one quantum bit. You cannot pack more data into a surface than the number of these pixels it contains. This imposes a fundamental graininess on the geometry of the universe. It means that at the very smallest scales, far beyond anything our most powerful instruments can probe, the smooth continuum of space and time dissolves into a discrete, digital-like structure. The universe operates with a finite information density. Think of a breathtaking digital photograph on your screen. From a normal viewing distance, the image appears perfectly smooth and continuous. You see gradients of color, soft edges, and lifelike detail. But if you zoom in dramatically, pressing your eye close to the screen, the illusion shatters. You see the individual pixels, the sharp, blocky squares of red, green, and blue that compose the whole. The beautiful, continuous scene was never truly continuous at all. It was an emergent property of a vast array of discrete points. Our experience of reality may be precisely the same. The seamless three-dimensional world we navigate, where distances can be divided infinitely and objects move along smooth curves, is the view from a distance. It is the macroscopic, emergent picture, but the fundamental architecture, the cosmic screen, is pixelated. The Planck area defines the size of each pixel. This discreteness has profound philosophical consequences. It challenges the ancient idea of the continuum, which has underpinned mathematics and physics for millennia. We have always assumed that between any 2 points in space, you can always find another point. You can keep dividing a length forever. But if space is pixelated, that is not true. There is a final, indivisible step. You reach a fundamental limit where the concept of between loses its meaning, much like you cannot have half a pixel on a digital display. This does not make our reality any less real, but it fundamentally changes what real means. The solidity of the ground beneath your feet, the emptiness of the night sky, the flow of time itself, all emerge from the collective behavior of an unimaginable number of these informational pixels, flashing and interacting according to quantum rules. The continuity we perceive is a magnificent and persistent illusion, a consequence of our macroscopic perspective. We are living inside the picture, not seeing the screen. This cosmic pixelation forces us to confront the grandest possible scale, the universe itself. If a black hole can be described by a theory on its two-dimensional horizon, could the same be true for the entire cosmos? This is the breathtaking and still speculative extension of the holographic principle into cosmology. Our observable universe, with its hundreds of billions of galaxies, its dark energy and its ancient light, may itself be a hologram. The screen for this grandest of projections is not a wall in space, but a surface in time, a boundary known as the cosmological horizon. Imagine you are standing in an ever-accelerating expansion, like our universe experiences. There is a point in the future, an ultimate horizon, beyond which light from distant galaxies will never reach you because space between you and them is stretching too fast. This is not a physical barrier you could touch, but a fundamental limit to information, much like the event horizon of a black hole. Some physicists propose that the entire history of our universe, everything that has ever happened or will happen within our observable sphere, is perfectly encoded on this spherical boundary at the infinite future. Our three-dimensional cosmic history, from the fiery Big Bang to the formation of stars and planets, would not be the primary reality. It would be the holographic movie projected from the data written on that ultimate screen. This idea is profoundly controversial because our universe, with its positive cosmological constant, is mathematically far more difficult to describe than the toy model universes where holography works perfectly. Yet, researchers are drawn to its potential power. They are applying holographic reasoning to the earliest moments, to cosmic inflation, that period of unimaginably rapid expansion thought to have set the large-scale structure of the cosmos. In this view, the inflationary epoch might not be a period of expansion in a pre-existing space. It could be the decoding process itself, the moment when the quantum information on the primordial boundary began to be projected into the three-dimensional geometry we now inhabit. The tiny temperature fluctuations we see in the cosmic microwave background, the seeds of all galaxies, would be the holographic imprint of quantum fluctuations on that early surface. This reframes our origin story in a deeply unfamiliar way. The Big Bang is no longer a singular explosion in a void. It becomes more like the starting gun for a cosmic projection, the moment the universe began to render itself from a lower dimensional code. While this remains a theoretical frontier without definitive proof, it represents the ultimate ambition of the holographic principle, to describe not just black holes or hypothetical spaces, but the entirety of our lived reality as an emergent, magnificent illusion. The holographic principle does more than reshape our physics. It unravels our deepest assumptions about existence itself. For centuries, the dominant worldview in science has been a form of materialism. This is the belief that reality is fundamentally made of physical stuff, solid objects and particles moving in a pre-existing space. Everything, from thoughts to emotions to the sense of self, is seen as a byproduct of complex arrangements of this matter. The chair is solid because it is made of wood and metal atoms. The mind is a process running on the hardware of the brain. This view places tangible substance at the foundation of everything. But what happens when that tangible substance, the very space those atoms occupy, is revealed to be a projection? The holographic principle strikes at the core of this materialist foundation. If three-dimensional objects are not fundamental, then the materialism based on those objects begins to look like a story told about the shadow, not the thing casting it. This does not necessarily point to anything supernatural, but it does force a dramatic shift in what we consider to be the bedrock of reality. Suddenly, the most promising candidate for that bedrock is not matter, but information, relationships, and the processing of data. This perspective finds a curious resonance with much older philosophical traditions, such as certain strands of idealism. Idealism suggests that reality is fundamentally mental or experiential in nature, that the world of appearances is a manifestation of mind or consciousness. While the holographic principle is not proposing a cosmic mind, it aligns with idealism in a structural way. Both frameworks assert that the world of tangible, separate objects in space is not the primary reality. It is a derived, secondary appearance emerging from something more basic and, in a sense, less substantial. In holography, that something more basic is a network of quantum information on a boundary. The principle nudges us toward an informational or relational ontology, where what is truly real are not things, but the connections and correlations between abstract data points. This leads us to the most profound and speculative frontier of all, the question of conscious experience. Our inner world feels vividly three-dimensional. We have a sense of spatial depth in our imagination. We navigate a rich mental landscape of memories and ideas that feel as expansive as the external world. The hard problem of consciousness asks why and how physical processes in the brain give rise to this subjective, qualitative experience. The holographic principle adds a new layer to this puzzle. If the physical brain, with its neurons and synapses, is itself part of a three-dimensional holographic projection, then consciousness is not just emerging from a physical object. It is emerging from an illusion. This suggests that perhaps conscious experience is not an extra ingredient added to the physical world, but is somehow intrinsic to the informational process from which the physical world emerges. Could the feeling of being a self located in a three-dimensional space be the very hallmark of a certain kind of complex information processing on the cosmic screen? It is a staggering thought, one that blurs the line between the perceiver and the perceived. We are not just observers of the hologram, we are patterns within it, and our awareness may be the process of that pattern experiencing its own projected reality. This is, of course, deep speculation, far from any scientific proof, yet it illustrates the sheer magnitude of the philosophical upheaval. The principle challenges us to consider that mind and world, subject and object, may not be as separate as we believe. They may be two aspects of the same emergent phenomenon, both born from the same quantum code. In this light, the mystery of consciousness might not be a problem to solve within the projected world, but a clue pointing directly to the nature of the projector. This philosophical upheaval inevitably draws us toward another modern idea about reality, the simulation hypothesis. Popularized by thinkers like Nick Bostrom, it suggests our universe might be an artificial construct, a sophisticated simulation running on some unfathomably advanced computer in a higher reality. The holographic principle echoes this notion in a haunting way, but it is crucial to understand they are not the same claim. The simulation hypothesis is a metaphysical speculation about who or what created our reality. It implies a programmer, a purpose, and a level outside our own. Holography, in stark contrast, is a physical theory emerging from the hard math of black holes and string theory. It makes no claim about creators or intent. It simply proposes that the fundamental nature of our universe is informational, and that three-dimensional space is not a primary ingredient but a secondary effect. One is a story about who built the computer. The other is a manual for how the computer, whatever its origin, actually works. Yet the parallel is undeniable and deeply provocative. Both frameworks insist that the world we experience directly, with its solid objects and vast distances, is not the base layer of truth. It is a representation, a computed output. In the simulation idea, it is rendered by silicon chips or quantum processors in another world. In holography, it is projected by the quantum entanglement of data on our universe's own boundary. Both point to information processing as the engine of reality. This conceptual overlap makes the simulation hypothesis feel slightly less like pure science fiction to some philosophers and scientists. If our best physical theories are telling us that the universe fundamentally operates like a cosmic computation, then the idea that such a computation could be engineered, rather than having arisen naturally, becomes a tiny bit more metaphysically plausible. It shifts the question from, is such a thing possible, to given how reality seems to be structured, could we tell the difference? The distinction remains vital, however. Embracing the holographic principle does not mean signing up for the simulation argument. You can fully accept that space is an emergent hologram without believing we are in some alien's video game. The principle describes the inherent architecture of nature itself, a universe that computes its own geometry from within. It is a property of reality, not an artifact of its potential creation. Still, this confluence of ideas forces a profound shift in perspective. We are asked to consider that whether the cosmos is natural or engineered, its deepest operating principle may be the same: the translation of information into experience. Our reality, in either case, is less like a place and more like a process, a constant, dynamic rendering of a world from a simpler, stranger code. Every revolutionary idea in science must face the scrutiny of its peers, and the holographic principle is no exception. While it offers a breathtakingly elegant framework, it exists within a vibrant and often contentious scientific debate, where alternative viewpoints and pointed criticisms help sharpen our understanding of what might truly be fundamental. Many respected physicists argue that the leap from a specific mathematical duality to a universal law of nature is premature, and that other paths to quantum gravity may be more direct or more likely. Their perspectives are not dismissals but essential counterpoints that test the resilience of the holographic vision. A primary criticism centers on the nature of the evidence itself. Skeptics point out that the most precise formulation of holography, the AD-SCFT correspondence, describes a universe that is mathematically elegant but physically unlike our own. Our cosmos expands with a positive cosmological constant, while the AD-S in AD-SCFT stands for anti-de Sitter space, a static universe with a negative constant. Translating the profound successes of this toy model to our real, accelerating universe is an enormous, unsolved challenge. Critics argue that until a de Sitter version of the correspondence is firmly established, claiming that our reality is holographic is an extrapolation beyond what the mathematics currently supports. It is like having a perfect map of a fictional continent and using it to claim you understand the geography of Earth. They might say, the map is beautiful and internally consistent, but it may not correspond to our actual terrain. Other physicists question the interpretation of emergence. The holographic principle states that space and gravity emerge from a quantum system without gravity. But some ask, could this be a mathematical artifact rather than a physical truth? The duality is a statement of equivalence between two descriptions. One could just as validly argue that the boundary quantum theory emerges from the gravitational bulk, or that neither is more fundamental. They are simply two different languages for the same thing. To claim the boundary description is the true reality is, from this viewpoint, a philosophical choice, not a conclusion forced by the equations. It is akin to arguing that a wave is more fundamental than the water it is made of, or vice versa, when both are valid descriptions of the same phenomenon. Beyond criticism of holography itself, there are compelling alternative frameworks for quantum gravity, each with its own passionate advocates. Loop quantum gravity, for instance, takes a more direct approach. Instead of making gravity disappear into a boundary theory, it seeks to quantize space-time itself. In this view, space is not a smooth continuum but a woven fabric of tiny, discrete loops. Geometry arises from the network of these loops and their intersections, like a cosmic mesh. Proponents of this approach argue it is a more natural quantization of Einstein's general relativity, providing a clear picture of a granular space without requiring an extra holographic dimension or a mysterious boundary theory. They see holography as a fascinating but potentially indirect detour. Another school of thought, causal set theory, proposes that reality is fundamentally a vast collection of discrete events. The smooth, continuous space-time of our experience is an approximation that emerges only when you look at a large number of these events and the causal relationships, the which came before which connections between them. In this framework, there is no pre-existing space or time, only a network of happenings. Advocates suggest this provides a more parsimonious foundation, building everything from the simple concept of causality without the need for the complex machinery of string theory or holographic duality. These competing visions highlight that the quest for quantum gravity is a field of rich diversity, not a single-minded march toward one idea. The debates are not about who is right or wrong in a final sense, but about which principles and mathematical tools will most reliably guide us to a deeper truth. The criticisms keep the science honest, forcing proponents of holography to refine their arguments, seek new predictions, and confront the hard fact that our universe is not an anti-de Sitter space. This dynamic tension is the engine of scientific progress. It reminds us that the most profound mysteries are not solved by consensus, but through a respectful and rigorous clash of brilliant imaginations, each trying to decode a reality far stranger than any one perspective can fully capture. So how does information actually become space? The mathematics behind this emergence is not about drawing new dimensions on a page, but about discovering them hidden within patterns of connection. Think of it as a kind of cosmic zoom lens. At the most fundamental level, physicists posit a microscopic theory, a set of rules governing the basic units, the quantum bits on the boundary. This theory is messy and complicated, filled with frantic, short-range interactions. But if you step back, if you mathematically average over countless tiny details, something remarkable happens. A new, cleaner description comes into focus. This process is known as renormalization group flow. It is the mathematical machinery for changing your perspective, for seeing what patterns become dominant when you stop looking at the individual trees and start seeing the forest. In this flow, the microscopic details, the specific identities of individual qubits, begin to fade into the background. What remains and grows stronger are the large-scale correlations between them, the collective rhythms of the entire system. It is from these persistent, large-scale patterns that new properties emerge, properties that were not written into the original microscopic rules. Temperature and pressure emerge this way from the motion of molecules. In the holographic context, it is the geometry of space itself that emerges. The mathematical flow, starting from the frenzied quantum data on the boundary, smooths out into the calm, curved equations of general relativity in the bulk. The dimension is not added, it is revealed. A powerful tool for visualizing this is a tensor network. Imagine a vast, intricate web of points, each representing a fundamental unit of information. These points are connected by lines, and each connection represents a thread of quantum entanglement. This web is the discrete, mathematical model of the boundary theory. Now ask a profound question. How much information is shared between two distant points in this web? To find out, you would not simply draw a straight line. You would trace the most efficient path through the network, following the strongest entanglements. The length of this optimal path, the minimum number of links you must traverse, is not just a number. In the emergent geometric picture, this path length becomes proportional to the distance between 2 points in the projected space. A dense, highly connected region of the tensor network projects as a tightly curved area of space. A sparse, weakly connected region projects as a vast, empty gulf. The three-dimensional volume of the emergent world is not a pre-existing container. It is a measure of the total complexity and interconnectedness of the underlying web. The mathematics shows us that geometry is not a stage, but a story, a narrative told by the relationships between the most basic pieces of reality. We are not living in a world of things that are connected. We are living inside the connection itself, a holographic manifestation of quantum correlation. The true power of a revolutionary idea lies not in its complexity, but in how clearly we can see its reflection in our ordinary world. To grasp the holographic principle, we need to step away from black holes and quantum equations for a moment and look at the familiar. Think of a grand old library, its shelves stretching into the shadows filled with countless volumes. Each book is a three-dimensional object you can hold with thickness, weight, and pages you can turn. Now open one. The story that unfolds in your mind with its castles, characters, and sweeping landscapes feels vast and immersive, a world with genuine depth. But where does that world truly exist? It is not in the paper and binding. It is in the specific, two-dimensional arrangement of ink on the flat pages. Every thrilling chase, every whispered secret, every description of a towering mountain is fully contained in those sequences of symbols. The three-dimensional experience of the narrative is a perfect holographic projection from the two-dimensional data on the page. The library itself, with its vast collection, represents the bulk of the universe, while the ink on all the pages collectively forms the boundary where the real information is stored. Or consider the immersive realm of a massive multiplayer online game. Millions of players log in to explore a seemingly endless, three-dimensional world, complete with forests, cities, and intricate architectures. They interact, form alliances, and embark on quests in a shared, persistent universe that feels tangibly real from within. Yet this entire sprawling cosmos is not housed in some giant, three-dimensional server room. It is generated and sustained by lines of code running on flat, two-dimensional arrays of silicon chips in data centers around the planet. The rules of the game world, the physics of how a sword swings or a spell is cast, and the history of every player's actions are all contained in that fundamental software layer. The player's rich, three-dimensional experience is a collective illusion, a real-time holographic projection rendered from the underlying, lower-dimensional computation. They are not literally inside the servers, they are inside the projection those servers create. To push our intuition even further, let us engage in a simple thought experiment, one we might call the case of the holographic princess. Imagine you have a most precious possession, a beautiful, intricate music box. Inside, a tiny, detailed figurine of a princess pirouettes to a delicate tune when you open the lid. One day, a curious and powerful friend asks to understand how it works. Rather than opening the box, you decide to explain it in a very strange way. You take a fantastically high-resolution scanner and meticulously map the entire surface of the closed music box, every curve, every decorative inlay, every microscopic scratch. You then send this immense data file, this perfect two-dimensional scan of its exterior, to your friend. With this data alone, and with a perfect understanding of the laws of physics, your friend could theoretically reconstruct not just the look of the box, but its complete internal structure. They could deduce the existence of the dancing princess figurine, the arrangement of the gears and the music cylinder, all without ever cracking the lid open. All the information about the three-dimensional interior is faithfully encoded on the two-dimensional surface. The princess is, in a very real informational sense, already on the outside. This is the quiet, counterintuitive heart of the principle. It suggests that if we possessed a complete enough description of the cosmic boundary, we would not need to peer into the universe to know its contents. We would already have them written in a different language on the surface of everything. This brings us to a profound and deeply personal question. Where do we, the observers, fit into this cosmic projection? If reality is a hologram emerging from information, then what is the nature of the one who is watching it? Quantum mechanics has long wrestled with the strange role of the observer. In its standard formulation, a particle exists in a blurry cloud of potential, a superposition of many possible states until it is measured. The act of observation, in some mysterious way, seems to force it to choose a single, definite reality. This has led to centuries of philosophical debate. Is consciousness somehow causing the collapse, or is something else, something more mechanical, at work? The holographic principle offers a fresh and startling lens through which to view this ancient puzzle. In a universe where everything is relational and informational, the observer cannot be a passive outsider looking in on a pre-formed world. The observer is part of the data, a pattern within the hologram. Its interactions are not disturbances to a fixed reality. They are the very process by which specific threads of the cosmic code become relevant and real. Think of a vast, interconnected network, the tensor web of the boundary. Every node is entangled with countless others, holding a near infinite number of potential stories. An observation is not a magic act. It is a specific kind of interaction, a query that travels along a particular path through this web. When that query is made, when a measurement occurs, it activates a specific set of correlations and deactivates others. The answer that comes back, the definite measurement we record, is not the only truth that was ever possible. It is the truth that became actualized through that particular relational event. In this view, the universe does not have a single, predetermined geometry waiting to be discovered. Different observers, by virtue of their different histories, locations, and interactions, might effectively be querying different subsets of the universal data. They are not seeing different projections of the same underlying movie. They are, in a sense, running slightly different renderings from the same source code. This perspective finds a powerful echo in modern interpretations of quantum mechanics, such as cubism, which stands for quantum Bayesianism. Cubism treats the probabilities in quantum theory not as objective properties of the world, but as an observer's personal guidebook, their best bets for what will happen when they interact with a system. The wave function is not a physical thing out there. It is a tool for an agent navigating a world of radical uncertainty. In the holographic framework, this makes perfect sense. The boundary quantum state is the ultimate objective source code, but any individual observer, being a localized pattern within the emergent projection, only has access to a limited part of that code through their interactions. Their personal quantum state, their wave function, is their partial map of the relational network from their specific vantage point within it. Another compelling alignment is with relational quantum mechanics, developed by Carlo Rovelli. This interpretation asserts that there are no absolute, observer-independent properties. Properties only exist in relation to other physical systems. An electron has spin-up only relative to a specific measuring apparatus, not in some abstract God's-eye view of the universe. This is the holographic principle in microcosm. If geometry itself emerges from relations, then all physical properties must too. There is no stage, only the dance. The observer and the observed are partners in that dance, and the steps they take together define the reality that momentarily crystallizes. This does not make reality subjective or solipsistic. The source code on the boundary is objective and shared, but the experience of the rendered world, the specific three-dimensional reality that feels solid and definite, is inherently perspectival. It is a view from within. You are not a ghost in the machine. You are a particularly rich and self-reflective pattern in the hologram, a knot of information so complex that it can form models of itself and its surroundings. Your observations are the process of this localized knot interacting with other knots, updating its internal model, and in doing so, participating in the continuous projection of the shared world. This offers a potential bridge, long sought by physicists, between the strange, observer-dependent rules of the quantum small and the definite, objective feel of the classical large. The classical world emerges not when things get big, but when the web of interactions and correlations becomes so dense, so stable, and so redundant that almost any observer query will activate the same set of reliable answers. The moon is there when no one looks because the informational pattern that projects the moon, is entangled with the pattern that projects everything else in such a robust, consistent way that its existence is a fixed feature of the relational network. In this holographic, relational cosmos, we are not separate from the mystery. We are expressions of it. Our quest to understand the universe is the universe's code becoming aware of itself, a strange loop in the cosmic computation where the output begins to study the program from which it emerged. The potential of this idea stretches far beyond solving textbook paradoxes. If the holographic principle truly describes the architecture of our universe, then mastering its logic could one day open doors to technologies that seem like pure magic to us today. The most immediate implications might lie in the realm of information itself. We live in an era of explosive data growth, where storing the digital footprint of our civilization requires ever larger server farms consuming vast amounts of energy. But holography teaches us that nature's own method of data storage is staggeringly efficient. A black hole, the densest object conceivable, stores its information not throughout its volume but on its surface. This suggests a theoretical upper limit to information density, but also a blueprint for ultra-dense storage. While we are light years from manipulating space-time to create data sinks, the principles could inspire revolutionary advances in materials science and quantum computing. We might learn to encode information in two-dimensional materials in ways that mimic this cosmic efficiency, leading to storage devices of unimaginable capacity housed in wafer-thin sheets. Computation, too, could be transformed. The universe itself, in the holographic view, is the ultimate quantum computer, where the projection of reality is the output. Understanding this process in detail might allow us to design computers that don't just calculate in a simulated space, but that use controlled quantum entanglement to literally construct geometric or gravitational answers to problems, a form of analog computation woven into the fabric of reality itself. Looking further ahead, the engineering of gravity becomes a tantalizing, if distant, possibility. If gravity is not a fundamental force but an emergent phenomenon, akin to the pressure in a fluid, then in principle it could be manipulated by engineering the underlying quantum state. We are not talking about anti-gravity plates, but something far more subtle and profound. The holographic framework shows us that spacetime geometry and gravitational effects are dictated by the entanglement structure of the boundary. In a highly advanced future, perhaps civilizations could learn to deliberately engineer quantum states on localized scales to create specific, stable spacetime geometries. This could lead to the creation of controlled, traversable wormholes, not by brute force, but by carefully weaving the correct patterns of quantum correlation to generate a bridge in the emergent geometry. Such a bridge would be the ultimate manifestation of the principle that entanglement creates connectivity. It would not be a tunnel blasted through space, but a connection summoned into existence by aligning information in just the right way, turning a mathematical equivalence into a physical doorway. Ultimately, these speculations lead us to the grandest scale of all, the ultimate fate of the cosmos. Our universe is expanding at an accelerating rate, driven by dark energy. In a future so distant it defies comprehension, all galaxies beyond our local group will have vanished over the cosmic horizon, their light forever lost to us. Stars will burn out and matter itself may decay. The universe will become a cold, dark, and incredibly lonely place. In this desolate far future, what happens to information, the fundamental currency of the holographic cosmos? This may be the principle's final and most profound implication. If the universe is a hologram, then its eventual heat death is not just the cooling of matter, but the gradual fading of the projection itself. As the cosmic horizon stabilizes and the universe approaches a featureless, maximum entropy state, the quantum system on the boundary may reach a state of equilibrium so perfect that no new information can be processed. The projection would become static, then dim, and perhaps finally silent. Yet, even here, holography offers a strange kind of solace. In this view, information is never truly destroyed. The complete history of our vibrant universe, every star that shone, every life that lived, every thought that was ever conceived, would remain eternally encoded on that final, frozen horizon. It would be a cosmic monument, not in stone, but in the immutable relationships of quantum data. The universe would not end with a forgetting, but with a perfect, permanent record. Our story, in its entirety, would become a single, timeless entry inscribed on the boundary of all that ever was. These grand visions rest on a foundation of deep and unanswered questions, the very puzzles that keep physicists awake at night. The holographic principle is not a finished theory, but a brilliant and demanding framework that opens new frontiers of investigation. The most pressing of these frontiers is the one we actually live in. Our real universe, with its accelerating expansion driven by dark energy, is described mathematically as a de Sitter space. Yet our most precise holographic dictionary, the Ad-SCFT Correspondence, was written for a different cosmos entirely, the static, inwardly curving anti-de Sitter space. Bridging this gap is perhaps the single greatest challenge in the field. Researchers are striving to construct a de Sitter version of the correspondence, a D-SCFT dictionary. This is not a simple translation. The nature of horizons in an accelerating universe makes the task extraordinarily complex, as if we are trying to read the source code for a movie while the screen itself is constantly stretching and changing size. Success here would be the ultimate validation, directly linking holography to the stars we see in our night sky. Closely tied to this is the mystery of time. We have discussed how space may emerge from quantum entanglement on a boundary, but what about the relentless forward march of time? In the holographic framework, the boundary theory is often portrayed as existing in a sort of timeless state, or with a time that does not directly match our own. How does the vivid, one-way flow of time we experience, with its clear distinction between past, present, and future, emerge from such a description? Some proposals suggest that time, like space, is a derived concept, emerging from the evolution of complexity or the processing of information on the boundary. It might be that our experience of time's arrow is tied to the gradual increase of entanglement, or the way quantum information spreads and becomes irreversible. Unlocking this would not just complete the holographic picture, it would touch on one of the oldest philosophical questions of all, the nature of time itself. Then there is the question of the microscopic ingredients. We speak poetically of the boundary as a vast quantum computer or a cosmic film, but what specifically are its fundamental parts? What is the actual stuff of the boundary theory? Is it a specific arrangement of strings and branes, as suggested by string theory? Or could it be something more abstract, like a vast collection of quantum bits interacting according to rules we have not yet fully discerned? Identifying these microscopic constituents is like trying to understand the circuitry of a computer chip by only observing the beautiful images it displays on a monitor. We see the glorious output, the projected universe, but we are still reverse engineering the design of the processor. This leads to the final, overarching question about the principle's universality. Is holography a general property of any consistent theory that successfully merges quantum mechanics and gravity? Or is it a specific, albeit beautiful, feature of certain formulations within string theory? In other words, is our universe holographic because that is the only way quantum gravity can work, or is it just one possible way among many? Answering this will determine whether holography is a fundamental law of nature or a fascinating feature of one particular cosmic blueprint. The research is alive with these challenges, each one a beacon guiding us toward a deeper understanding of where and what we truly are. The idea that information might be the true bedrock of reality resonates far beyond the equations of physics. It echoes through other fields of science, whispering a possibility of profound unification. This is not about reducing biology or thought to mere physics, but about recognizing a shared, deeper language that might describe patterns across nature. If the cosmos is a hologram projected from information, could the same kind of logic shape the living world? Consider the elegant discipline of information theory founded by Claude Shannon. Its original goal was practical, to measure and optimize the transmission of signals across telegraph or telephone lines. Shannon defined information not by its meaning, but by its surprise value, its ability to reduce uncertainty. A message that is completely predictable carries little information, while a rare and unexpected one carries a lot. This abstract concept became the foundation of the digital age, the ones and zeros that power our computers. Yet, its implications run deeper. Information theory provides tools to quantify complexity, pattern, and organization in any system. Researchers now use these tools to analyze the human genome. The sequence of DNA bases in our cells is not random. It is a highly ordered, information-dense code, a blueprint written in a 4-letter chemical alphabet. The amount of information in this code and how that information is structured and regulated is central to life itself. When a cell differentiates into a skin cell or a neuron, it is not acquiring new DNA. It is selectively reading different chapters of the same informational book, activating specific patterns of genes. From this perspective, the process of evolution by natural selection can be seen as an algorithm for information processing. Over deep time, random mutations introduce new data into the genetic code. The environment acts as a kind of cosmic query, testing that data. Sequences that enhance survival and reproduction get copied and stored, while less effective ones are filtered out. The biosphere becomes a vast, distributed memory system, accumulating and refining information about how to persist in a changing world. This is not a literal hologram, but it is a system where complex, three-dimensional organisms, with their intricate forms and behaviors, emerge from the one-dimensional string of data in their DNA. The parallel to the holographic principle is structural, a reminder that rich, layered reality can unfold from a simpler informational core. This lens can even be turned inward toward the mystery of cognition. The human brain, with its nearly 100 billion neurons and trillions of connections, is arguably the most complex information processing system we know. Your conscious experience, your memories, your sense of self, all arise from the electrochemical conversations within this neural network. Neuroscience tells us there is no single seat of consciousness in the brain, no central processor. Instead, awareness seems to be an emergent property of the whole system's integrated activity, much like the three-dimensional image emerges from the entire holographic film. Different aspects of a single memory, for instance, are stored in disparate regions of the brain, woven together not in one location, but through the pattern of connections between them. The memory exists as a relationship, a specific pattern of correlated information across the network. Damage a single area, and the memory may become fuzzy or incomplete, but it is rarely erased entirely because the information is distributed, not localized. This is a hallmark of holographic storage, where every piece of the film contains information about the whole image. The brain's resilience and its capacity for associative thought, where one idea effortlessly triggers another, bear a striking resemblance to this kind of distributed, relational encoding. Viewing mind and biology through an informational and emergent lens does not diminish their wonder, it reframes it. It suggests that the universe may employ a common strategy across vastly different scales, from the fabric of space-time to the fabric of thought. In each case, tangible, complex reality is not the starting point. It is the magnificent and persistent output of something more fundamental, a constant conversation of data following elegant, discoverable rules. This points toward a future where physics, biology, and cognitive science might not just borrow metaphors from one another, but might eventually share a common foundational understanding, all speaking in the quiet, powerful language of information. But this elegant mathematical framework inevitably draws a skeptical gaze. A compelling counterargument suggests the entire holographic principle, especially its cleanest expression in the ad-SCFT correspondence, is just that, a mathematical correspondence. It is a breathtakingly useful trick, a computational shortcut for solving difficult problems, but not a description of what our universe actually is. This is a serious and respectable position. The duality lives in the pristine world of equations, describing hypothetical universes with perfect symmetry and negative curvature, conditions our own cosmos does not meet. From this viewpoint, claiming our three-dimensional reality is an illusion is like using a perfect map of a fictional continent to declare the Earth is flat. The map is a powerful tool, but it represents a different terrain. The strength of this skepticism lies in its caution. It reminds us that not every beautiful mathematical relationship needs to be a law of nature. Yet, there are reasons to believe the holographic principle points to something more than just a clever calculation. Its power is not born in abstraction, but in its ability to resolve concrete, physical catastrophes. Consider the black hole information paradox again. This was not a minor puzzle, but a fundamental crisis that threatened to invalidate either quantum mechanics or general relativity, the twin pillars of modern physics. The holographic principle did not just offer a different way to calculate, it offered the only coherent escape from an impossible choice. By shifting perspective to the boundary, it showed how information could be preserved without violating any known law. Solving a paradox of such profound physical consequence suggests the idea is tapping into something real about how gravity and quantum information must coexist. Furthermore, the principle's roots are not in string theory alone, but in the undeniable thermodynamics of black holes. Jacob Bekenstein and Stephen Hawking's discovery that a black hole's entropy is proportional to its area was a result about real, physical objects in our universe, derived from combining quantum theory with gravity. The holographic principle grew directly from trying to understand what that bizarre area law truly meant. It is an interpretation of a hard, physical result. When Ted Jacobson later derived Einstein's equations of gravity from thermodynamic principles applied to any horizon, he reinforced this. He started with the physical concept of heat and entropy, concepts as tangible as a steaming cup of coffee, and showed they inevitably lead to the equations that describe the curvature of the cosmos. This thermodynamic emergence of gravity feels less like a mathematical coincidence and more like a deep clue about the universe's operating system. It hints that gravity is not a fundamental force in the traditional sense, but a collective, statistical behavior, much like the pressure of a gas emerges from the motion of molecules. The holographic principle provides the most complete framework for understanding how that could possibly work, by showing exactly what the molecules might be, quantum bits on a boundary, and how their collective state projects the force we call gravity. So, while the specific ad-SCFT dictionary may be a perfect model of a universe that is not our own, the general principle it embodies seems to be answering urgent questions posed by our own physical reality. It moves from being a convenient map to being a candidate for the very legend that explains all maps, a theory of how geometry itself is drawn from more fundamental data. The mathematics is not a trick but a language, and it is telling a story about where space, time, and even our own place within them might truly come from. The pieces of the puzzle now lie before us, waiting to be assembled into a single, startling image. We began with a paradox at the edge of a black hole where the rules of reality seemed to tear. We followed the trail through thermodynamics, where gravity itself emerged from principles of heat and disorder. We explored a mathematical duality where a world with gravity is perfectly mirrored by a flat, quantum world without it. And we saw how the strange glue of quantum entanglement might weave the very fabric of space. These are not separate stories, they are different perspectives on one profound revelation. Our vivid, three-dimensional cosmos, with all its solidity and depth, is not the foundation. It is the grand finale, a magnificent and coherent illusion emerging from a simpler, flatter, more fundamental reality. To see how this synthesis works, let us step back and watch the illusion assemble itself, layer by layer. At the absolute base, the bedrock of everything, there is no space, no time, no gravity. There is only information. Think of it as a vast, silent ocean of quantum bits, each holding a simple yes or no potential, existing on an unimaginably distant two-dimensional surface. This is the cosmic boundary, the ultimate screen. On its own, this sea of data is static and featureless, but then a relationship forms. Through the rules of quantum mechanics, these bits become entangled. A connection is established, a correlation where the state of one bit instantly influences another, no matter how far apart they seem in the projection to come. This is the first stitch in the tapestry. Now multiply that connection by an astronomical number. Not just pairs, but vast, intricate networks of entanglement form across the entire boundary. These are not random links, they follow the logic of the underlying quantum theory, creating a complex, humming web of correlated information. This web has a property we can measure, a kind of quantum disorder or possibility, known as entropy. And here is where the magic of thermodynamics enters. This entropy, this measure of the hidden information in the web, is not just a number. When we apply the universal laws of thermodynamics to it, asking how this system behaves as a whole, something incredible happens. The mathematics of heat and energy applied to this entangled web spontaneously generates the equations of general relativity. The statistics of the quantum connections give rise to the smooth, curved geometry of space-time. Gravity is not a force added to the system. It is the natural, large-scale behavior of the system itself, much like the pressure of a gas emerges from countless molecular collisions. So, from information and entanglement, we get geometry and gravity, but geometry needs dimensions. How does the flat web project a world with volume? This is the final, crucial step of emergence. The strength and pattern of the entanglement in the web define distance. Two bits that are deeply, directly entangled in the web when the mathematics is translated, appear close together in the projected world. Bits that are only weakly or indirectly linked appear far apart. The entire dense, interconnected structure of the web, when viewed through the right mathematical lens, unfolds into a consistent, three-dimensional picture. The volume of a region in our world corresponds to the total complexity and richness of the quantum connections in that part of the boundary web. A star, a planet, a human being, these are not clumps of special stuff in the projection. They are stable, incredibly intricate patterns of correlation on the screen, patterns so coherent and self-reinforcing that they project as persistent, solid objects in the holographic movie. This is the synthesized illusion, a silent, flat quantum computer humming with entangled data processes its own state. The act of that processing, governed by thermodynamics and quantum logic, projects the consistent experience of a three-dimensional universe, complete with gravity, stars, and observers. It is a self-consistent mirage of breathtaking complexity. To call this fake misses the point entirely. The illusion is real in every way that matters to us within it. Its laws are consistent, its history is coherent, and our experiences within it are genuine. The revelation is that its fundamental nature is different and richer than its apparent structure. It is akin to understanding that a living cell is not merely a bag of chemicals, but a dynamic, self-sustaining process of information flow. The chemicals are real, but the life is in the pattern and the process. Our universe is real, but its reality is not made of space and matter in the way we instinctively feel. Its reality is made of relationships, of information in conversation with itself, weaving the persistent dream of a world. We are that dream, becoming aware of the loom. So we have traveled from the silent, absolute stage of Newton across Einstein's dynamic fabric and into the quantum fires of a black hole's edge. Each step revealed a deeper, stranger layer, peeling back our assumptions about the world's solidity. We stood before a paradox that threatened to unravel physics itself, and found our escape not by looking deeper into the volume of space, but by turning our gaze to its surface. The journey has led us here to a quiet but monumental realization. The three-dimensional world we navigate, with all its tangible depth and distance, is not the foundation of reality. It is the grand and glorious projection. Space itself, the very arena of existence, is a magnificent and persistent illusion, emerging from a vaster, simpler, and flatter truth. That truth is a cosmic sea of quantum information, humming on a distant boundary where every bit of data is entangled with every other in an intricate, shimmering web. The force of gravity, the geometry of the cosmos, and the very feeling of moving through a volume are all collective effects, the statistical shadows cast by this underlying quantum conversation. We are not beings moving through a pre-built universe. We are patterns within a cosmic computation, experiencing the breathtaking output in real time. This transforms our quest to understand reality from a search for the smallest particles to a deciphering of the most fundamental relationships. It asks us to consider that the universe is not a place where things happen, but is itself the happening, a constant, dynamic process of information becoming experience. The mystery is far from solved. The equations for our own accelerating cosmos are still being written, and the debate among brilliant minds continues with fierce passion. But that is the beauty of the search. It invites all of us to wonder, to question, and to look at the night sky not just as a vast emptiness, but as the most convincing and beautiful mirage imaginable. What do you think lies beyond the illusion? Share your thoughts and questions in the comments below, and for those who wish to delve deeper, the journey continues in the descriptions and the quiet, relentless work of science.